Hello and welcome to FlowVision video demonstration series. In this session we will be focusing on the workflow to prepare a dry screw compressor calculation. We will be covering the process starting from the CAD import to FlowVision until the beginning of the calculation, including the first iterations. This whole process should take around 30-35 minutes, including the mesh generation. So let's go ahead and click on create a new project icon and select the main geometry, in this case the casing geometry of our compressor. Okay, now let's specify the working folder, screw compressor example 1. So now we have the casing geometry. We can see it on the graphics window. As you see, we don't have the rotors yet, so let's go ahead and import those objects as well. Let's start with the male rotor. Okay, now we have the male rotor in FlowVision. We can change the name to imported object male rotor and import the female rotor as well. Okay, now we have the female rotor as well. Let's immediately change the name, female rotor. Perhaps now we can jump to post-processor tab for a second and change the visualization settings of these objects to see them better in the graphics window. Now they seem better, I think. Let's turn the perspective view off. So in FlowVision, usually when we start the project, the first thing to check is the source file to make sure that we're using the right file at the right location. Here we can also check other information about the CAD we supplied to FlowVision and the tolerance value. Next, we can check the reference values that we're going to use in this project. The reference temperature and reference pressure. We should modify them if necessary, but for this project we're going to use default values. In FlowVision, most of the time we use the items from top to bottom to build our project. So let's go ahead and create a substance and let's load it from the standard database. We're going to load air, gas equilibrium, and click on OK. As you see, we have loaded the data from the standard database. For density, for example, it tells me that we're using the ideal gas law, but of course, if it's necessary to type in a constant or formula or table, this is also possible. So now let's create a phase. It should be continuous phase. Let's change the name first, phase air, and let's assign the substance that we created in the previous step. I click on OK. Now the next step is to specify physical processes in this phase. I'm going to turn on the heat transfer equations for compressible flow. Motion should be specified as Newtonian fluid. For the turbulence in this project, we're going to use K epsilon FlowVision model, which is slightly different than standard K epsilon model. Let's click on apply. Here there are various advanced settings for each physical phenomena that we specified in this item: heat transfer, motion, turbulence. I'll highlight the option all terms here in the heat transfer item. This corresponds to the heat generation due to viscous dissipation. For the time being, we will leave this option as no, and we will start our calculation. And once we achieve the convergence with this configuration, we will come back to this page after pausing the calculation. We will change this setting to yes, and we will include the heat generation due to viscous dissipation, and then we will continue the calculation and arrive the convergence with that configuration. This is a step to take in order to increase the efficiency to achieve convergence. The other items, we're going to leave them as they are in the default settings. So now our phase is ready. Next should be creating a model. Let's call this model as model air. Here, since this is a screw compressor and we have leakage flows that we would like to resolve, we need to activate the gap model. Once we activate the gap model in FlowVision, it adds an item here, standard gap model, and asks minimum and maximum clearance values. Depending on these values, FlowVision will activate or deactivate the gap model in certain locations during the calculation. So here I'm going to leave the maximum clearance as it is, but change the minimum clearance as 0.1 micron. I click on apply. So next we need to specify the phases in this model. Let's assign the phase air that we created to this model. Phase interaction we don't have. We're going to deal with the initial data later after we create the boundary conditions. So now our model is ready. We can now go to subregions, subregion 0, and change the name of the subregion to subregion air. And let's assign the model that we created to the subregion. The next step here should be telling FlowVision that the rotors that we imported, they are actually rotating. So for that we need to create modifiers. There are a bunch of modifier types in FlowVision. We're going to pick moving body modifier type on the objects that we would like to have them rotating. So let's click on male rotor and click on OK. Now FlowVision has the male rotor as a moving body. Let's change the name to moving body male rotor. So let's do the same thing to female rotor. Again, let's change the name. Moving body female rotor. I click on apply. So now we have created the moving bodies for these components. Now it's time to specify the details of this rotation, mainly the center of inertia and rotation speed. Now I have to check my notes to type these data in. 0.1. Let's go to rotation speed, radians per second, 0 minus 723. I click on apply and go to female rotor and type in the data we have. Minus 0.12 0.0285935, and the positive of this number for the y-axis, and 0.1 for the z-axis. Let's type in the rotation speed as well. 0 plus 482 radians per second. So let's check this data. This one looks fine. This one looks fine as well. Okay, now everything seems fine. So now FlowVision knows that these components are actually rotating. Next thing is creating boundary conditions. As you see, FlowVision automatically created some boundary conditions here. As you see, they are in different colors. This is because they were drawn like this in the CAD environment. So FlowVision automatically says that, okay, this is a different boundary condition because this has a different color. So let's go to boundary condition 0 and change the name of this boundary condition to casing. This is a wall type of boundary condition. It seems correct. The boundary condition number 1 is evidently the inlet boundary condition. Let's change the name. Inlet and inlet outlet. And we need to specify the velocity as inlet pressure. Click on apply. And go to boundary condition number 2. It should be outlets. And we need to give the free outlet type. And we're going to specify the pressure. Boundary condition 3 and 4, they are the rotors. So let's change the names. Male and female. So let's specify the details for the inlet and outlet boundary conditions. The temperature should be 20 degrees centigrade. Velocity should be 0 because this corresponds to the atmospheric pressure. Pulsations 0.01. And the scale should be 0.001. So let's go to outlet boundary condition. The velocity should be 200,000 pascals. Let's recheck these values again. 20, 0, 0.01, 0.001. Everything seems fine. So now it's time to give the initial data. We're going to define the initial data here as initial data 0. But later on we're going to assign this data to a specific location in the computational volume. We're going to import an object which covers the outlet section of our machine, and we're going to assign this initial data number 0 that we create to that volume, and the rest of the machine will be using the reference values for the initial conditions. So here the temperature is 100 degrees centigrade. Velocity, we don't touch the velocity. Pressure should be 200,000 pascals. And these should be left as 0. So now we have defined the initial data, we need to import the object that we're going to use to initialize this data. Let's import the initialization box. As you see, this box is covering the outlet section of our machine. So let's go to subregions, subregion air, initial conditions. As you see, the initial data number 0 is assigned to the whole computational space. We're now going to change it to imported object number 0. And actually, let's go to this object and change the name of this object to initial data box. So right now it's time to go and create the computational grid, but let's go to the post-processing tab for a second and hide this object, not to see it all the time. Okay, as you know, in FlowVision we first create an initial grid and then we create adaptations based on either solutions or geometries. The geometries can be arbitrary geometries or the real geometries that we use in the calculation. So let's pick the initial grid editor here, but before that let's change the view so that we can look at the x-axis while we prepare the initial grid, because we will have a variation on this axis. So let's add a reference line here and drag it to a location close to the rotors. And now I'm going to specify the minimum grid size as 0.01 meters and relax the maximum grid size so that we can let FlowVision calculate the maximum grid size based on the minimum size that I give and the expansion rate. So now I'm going to draw the profile, and we can observe here on the graphics window. I'm drawing this profile by moving these little dots on the reference lines. So as you can see, the divisions close to the outlet section, they are larger than the divisions close to the rotors. And the intention is to create almost cubic cells near the rotors where the action is going to take place. So here we gave 0.01 meter for the minimum cell size. I'm going to do the same for Y and Z axis, but here we're going to use a constant profile. So as you see on the y-axis we have constant cell size, which results in cubic cells. Once we do this for the z-axis as well. There we go. So now we're done. When I click OK, FlowVision tells me the total number of cells and a quick summary about the mesh that we just created. I click on OK and click on Apply. So now this is my initial grid. It's time to create our adaptations based on the arbitrary geometries that we're going to import. So let's select adaptation rotors box. Let's change the name first. Adaptation big box. Click on apply. Here, as you see, this box is covering the two rotors. Let's create an adaptation on this box. Let's write adaptation big box, and the object should be, of course, adaptation big box, and maximum level should be 2. So one level of adaptation in FlowVision means that the initial grid will be divided into 8, and this process will be repeated 2 times when I pick the maximum level of adaptation as 2. Let's go ahead and import the other object that we're going to use for the adaptation. Adaptation rotor to rotor box. Let's change the name of this object, adaptation small box. I click on apply. As you see, this box is at a location where these 2 rotors are meshing into each other. We have this object there because this is a critical location for this calculation. So let's go and create another adaptation on this small box. Adaptation small box. The object should be small box, and the maximum level will be 3 in this case, which means that the division process will take place 3 times. So now we have the adaptations as well. The next step is to specify the solver parameters. But before that, let's go to Postprocessor tab and hide these boxes that we imported so that we don't see them on the graphics window. And for here in the solver tab, in the time stepping, we're going to use the CFL condition. Apart from the convective CFL, we're going to activate and use the surface CFL, which is used when we have moving bodies in the calculation. If you remember, we have specified the rotors, the male and female rotor, as moving bodies in the subregion. That's why we need to activate the surface CFL and use it together with the convective CFL to achieve the right time stepping. Let's add the residuals to the monitor to track the convergence. And the advanced settings, we're going to leave them as they are. We're going to use the default settings in this calculation. So next, we need to log in and connect to a solver. I log in, and before that, I just save the project and run a new solver, connect to the solver, and if everything is fine, FlowVision will tell me that we have established the connection. Okay, now everything seems fine. Right now I'm going to click on the Go button. Now our calculation is running. We're waiting for the first iteration. Here, while waiting, we can go to the Postprocessor tab and create some items in order to see the details of the computational grid, for example, or to see the gap cells. Let's go to plane 0 that FlowVision created beforehand for us and change the normal of this plane to have a look at the YX plane. There we go. We also need to shift this plane a little bit. Let's try, and there we go. We can even reduce it to 0.9. Okay, now we have a plane cutting the machine from the YX plane. so that we can now have a look at the computational grid on this plane, or we can have a look at the pressure distribution, for example. Since this session is not focusing on the post-processing, we are not going to cover these kind of aspects, but we will have a look at the computational grid, we'll have a look at the gap cells, etc. And the post-processing session will be a separate session. So let's click on apply and right click on this plane and create a layer of computational grid section. I click on OK. There I have this item computational grid section number 0 on plane 0. This means that once the first iteration arrives, we will be able to see this computational grid section. So let's go ahead and create another layer of cell set, and in this cell set I have to specify the cell type, and it should be gap cells. So I click on apply. In FlowVision, when you create an item like this, they are automatically visible. So hide and select hide to hide. So let's go to computational space and create another layer of cell set, and this cell set is for the whole computational space, not on the plane 0. So let's again select gap cells. Okay, now we're ready for the first iteration. We can calmly have a coffee and wait for the first iteration to arrive. Then we can have a look at the computational grid section. If we don't like something, we can go back, we can pause the calculation first. We can go back to a preprocessor and modify and continue the calculation. So there we have our first iteration, and apparently we can see the computational grid section that we created. Let's hide the solid object so that we can focus on this plane. Geometry, hide yes, moving bodies, hide yes. So now we can see it better. Let's see if our adaptations are fine. This is the big box adaptation, the level 2 adaptation, and this is the level 3 adaptation on the small box at the location where these two rotors are meshing into each other. Let's have a look at the clearance. Here we're working on a small laptop for this demonstration. It's a 2.4 gigahertz and 8 gigabyte memory laptop. That's why we have a coarse grid, otherwise I wouldn't be able to record this video for you. There we have the second iteration. We have the total cell count for 400,000. Let's unhide this computational grid section and click on the cell set 0 to see the gap cells. If you remember, we had specified in the models, we specified the standard gap model parameters, minimum and maximum clearance. Here, when the clearance is between those thresholds, FlowVision automatically says that okay, this is a gap cell, so I'm going to activate the gap model, and these are the cells for this time step, the gap cells that are used. So let's have a look at the cell set number 1, which is the cell set of gap cells in the whole computational domain. Let's hide this computational grid section and also unhide the rotors. And actually we can hide this plane as well. Okay, now. And there we have the gap cells in the whole computational domain. As you can see, these cells are corresponding to the cells where we have the leakage flows. So this is an efficient manner to resolve the leakage flows.